Hi, my name is Chris Schulte, and today we're talking about lab number 2, the topic of magnetic field of a bar magnet. The purpose of the lab was to measure the distance dependence of the magnetic field due to a small bar magnet, and then compare the measurements to the distance dependence predicted by the equations for the on- and off-axis magnetic fields derived from the Biot-Savart law. The goal of the lab was to utilize a dedicated magnetometer app, not the compass app, to measure the magnetic field due to a permanent dipole magnet, and then compare the predicted values derived from the Biot-Savart law. Some fundamental physics principles and models used in this lab include the Biot-Savart law, which describes a magnetic field generated by a constant electric current. It relates the magnetic field due to the magnitude, direction, length, and proximity of the electric current. Here we see the value of the magnetic field, and as well as the relation that the magnitude taken with the natural log is equivalent to the natural log of k plus n times the natural log of r. The distance dependence of a bar magnet states that as the distance from the source increases, the field strength decreases. Conversely, when the bar magnet moves closer to the source, the magnetic field strength decreases. This is shown by the equation that the magnitude of the magnetic field of the bar is equivalent to capital K times r to the n. Overview of results. The system in this lab was a magnetometer and magnet, while the surroundings was Earth's magnetic field. Results. As the magnetometer moves closer to the magnet, the measured x component of the magnetic field also increases. The n value was calculated to be negative 2.9316 meters, and the magnetic dipole was calculated to be 2.4375 am squared. Data and analysis. The initial conditions for the experiment included the phone being properly aligned to the magnetic north at the location of the experiment, which was Atlanta, Georgia. Here, the net magnetic field is approximately 48.6 microteslas. No additional magnetic fields were present when doing this lab, and we can see the setup of the phone, magnet, and meter stick in these two figures on the screen. Here we see some data for the on-field and as well as the generated graph. We see that the average R as well as the average B in the x direction was calculated from 3 independent observations, which then we are able to create the natural log of R by natural log of B in the x direction graph. From this, we were able to take the line of equation of best fit. From this equation, I was able to determine the value for n, which is equivalent to negative 2.9316, or the slope, and we were able to calculate k by taking e to the value of the y-intercept, so e to the negative 14.534. When calculating the dipole moment of and off-field data, we were able to use the various equations of the Biot-Savart law and the relationship of a bar magnetic field. Here we were able to calculate the dipole moment to be 2.4375. We also have off-axis field data, including dperp, the magnitude of the magnetic field by Earth, as well as some other figures that we were able to calculate. Here we see the computational model, or the glow scripts code, including the constant u over 4 pi, which is 1 times 10 to the negative 7th. We were able to create the magnet at the origin, as well as a function for the magnetic field, which is defined by the function dipole b, with inputs mu and r. Then we took the average dperp from the experiment, and then created an observation location at 45 degrees from the axis to get some various information. We then created, for the computational model, observation locations, 2 of which were on axis and 4 of which were perpendicular to the axis. From this, we were able to generate the following output. Here we see that the value for D was calculated to be 0.261205, and B at 45 degrees at distance D was equal to 6.83863 e to the negative 6, 2.05159 e to the negative 50. We see here that the comparison between the experimental and computational values were similar. However, there are some inconsistencies. Conclusions. The big main ideas and takeaways are included the interrelationship between the Biot-Savart law, distance dependence of a bar magnet, and superposition. These three state that the magnetic field created by a constant electric current relates to magnetic field due to magnitude, direction, length, and proximity of the current, as well as the fact that at the distance from a source increases, the field strength decreases. Superposition tells us that the resultant electric field is a vector sum of the electric field due to individual charges. Some assumptions in error analysis that could account for the slight inconsistencies between the experimental and computational values are that there were inaccuracies in the magnetometer app on the iPhone, potential human error when utilizing the meter stick, and potential interference from other magnetic fields. We also assumed that the x-axis was defined by the magnetometer app that points along the width of the phone, the y-axis points along its height, and that z-axis points out of the screen. Since all the above assumptions and generalizations made, there is likely a slight error in the calculated observed values despite controlling as many variables as possible and being precise in measurements. What if? If we had oriented our setup so as to not compensate for magnetic north, my results would have had a large error as the Earth's magnetic field will skew my measurements of the magnetic field created by the magnet. Therefore, all calculated values would be less accurate. If we instead had two identical magnets then stuck together end to end, the measurements would differ, although the direction of the fields would remain the same. Instead, they would double in magnitude because the two mags would mimic a single larger magnet. Thank you.